electrons. The electrons are going from a higher energy state to a lower energy state, so that means that they're going to be giving off energy each time they move from one molecule to another. Okay, so now we're going to introduce a little coenzyme. I told you we'd give you some real life examples here. So this little coenzyme, you guys heard of niacin? Niacin, it's a common vitamin. Again, you can go to your drugstore, Kroger, find it in the pharmaceutical section. So you have to have niacin in your diet. So in the process of cellular respiration, we're going to have glucose or any other molecule you want to pick, and we're going to break it down in a series of steps. Why do we want to break it down in a series of steps? Why wouldn't we want to just break it down all at once?
Because it's too willy-nilly, and like the cell wants organization.
Yes. Well, it's something like that. If we just spontaneously combust sugar and just we have like an explosion of sugar, which honestly, if our bodies were hotter, we could burn sugar. You know, if you think about when you burn sugar on like a creme brulee, you can burn sugar and it will give off energy, but our bodies aren't hot enough to start to get over that energy of activation barrier, so we need these enzymes to do it. But if we had an enzyme that did it all at once and it was spontaneous, that would be problematic because it's hard to harness energy from an explosion. It's pretty destructive. So if we take it and instead of just, you know, combusting our sugar molecule, you know, can you imagine if you ate something and immediately it turned into fire in your body? That's scary. So instead of just combusting a sugar molecule, we take a series of enzymatic reactions and in a stepwise fashion, we reduce it. We change this electron distribution, and each time we do that, we can better harness the energy that's released in each subsequent step. So it's a much more efficient way of grabbing energy from the process. So if you think about it, does anybody know what rocket fuel is? Take liquid hydrogen and liquid oxygen, mix them together with a little spark. Spark provides that energy of activation. You can send something into orbit with the amount of energy that gets released from some of these reactions. So it's good that we're not hot enough to get over that energy of activation barrier, or we would just spontaneously combust. But we do need these enzymes to allow these processes to occur in a more rapid way than they would if they were just had to occur without enzymes. But we also need to control them so that we can harness the energy more efficiently by doing it in a stepwise fashion. Okay? Anybody ever seen one added chlorine to a pool before? Okay, so chlorine is another really good oxidizing agent. Remember, it has 7 electrons. It really wants to grab another one. So if you take chlorine and you sprinkle it in your pool, you're fine because there's a lot of chemical reactions that are going on there. It's actually a little bit more complicated than just being an oxidizing agent. But there's all of the heat that's given off can be absorbed by the large body of water. If you take a bucket and you put a couple of pounds of chlorine in the bucket, and instead of sprinkling the bucket chlorine in the water, you just take water, push it, and sprinkle it on the chlorine and mix it up, you will be in the hospital with a catastrophic burn. You will set off an explosion because the amount of water, if you pour a small volume of water on a couple of pounds of chlorine, the amount of the heat that's given off in that chemical reaction will cause an explosion versus if you sprinkle it in the pool, the heat that's given off can be absorbed by the large body of water. So that's why if you're ever adding chlorine to a pool, sprinkle the chlorine in the pool, not water on the chlorine. You will be in the hospital. So these are important things that people don't tell you. Save a limb, save a burn, keep you guys safe. But it all has to do with the energy that's given off in all of these common reactions. And that's what fuel is like, you know, when you put gasoline in your car, you know, if you're standing there and you have the gasoline and you're pumping your car, there's oxygen in the atmosphere, you're putting these hydrocarbons that are high energy bonds into your car, but they don't spontaneously combust. But if you're smoking a cigarette and you're putting gas in your car, are people going to look at you like you're crazy? Yes, they will, because now you're putting energy in terms of heat from the cigarette and the fire next to a chemical reaction, so you're providing the energy of activation to start that chemical reaction and cause an explosion. That's why hopefully you don't smoke anyway, because it's not good for you. But if you were to smoke, don't smoke next to, fuel in the presence of oxygen, okay? Because you give it that activation energy to cause the reaction to proceed, but if you don't get it over that energy of activation barrier, you're safe. But when it's in your, that's what's happening in a combustion energy. You're adding little sparks to hydrocarbons to generate enough energy to drive your car. That's a lot of energy in a small quantity of hydrocarbons. So imagine that energy getting broken down in our own bodies. Okay, so what we need in order to do this is have this little coenzyme called NAD. Stands for nicotine adenine, or nicotine adenine, I can't even pronounce it all, adenosine dinucleotide, and it's a coenzyme. So again, it's one of those little organic cofactors that we need in order for the enzyme to work correctly. And the reason that NAD is so useful in this role, this little electron acceptor, is that it's really easy for this little molecule to switch back and forth from its oxidized to its reduced form. So it can really quickly switch back and forth between being oxidized and being reduced. So it can grab an electron, hold on to it, and then let it go again without a great deal of energy loss. So you lose a small amount of energy in this transfer, but it's very, very minute compared to the overall. So it's kind of like, will you hold this for me for just a second? I need you to just hold on to it, and then I'll ask for it back. And it's like, sure, I'll hold it, and here you go. That's what this little coenzyme is doing. It holds onto the electrons as they're getting transported down the chain, and it helps transition from one compound to the next. Okay, and so NAD is constantly going to be going back and forth between, what would it be considered oxidized or reduced when you see that plus mark there?
Oxidized.
I'm going to take my little thing off.
It's oxidized, right? Because it lost the electron.
Sorry, I shouldn't have erased that. So if it's got a
It's
positive charge,
oxidized.
that means that it has one less electron, so it's lost an electron, so it's oxidized. People always write that on the test. When I think oil rig, I can see it at the top of every test. And so once it grabs an electron, it gets switched to NADH. So once it's switched into this form of NADH, it's considered reduced. And that basically is the stored form of the energy that then gets converted into making ATP. So we'll go into more detail. It might not make much sense right now, but we'll be giving a special role for NAD. But for the point now, just know that it goes back and forth very easily between its oxidized and reduced state, and it just helps hold onto the electron as it's getting moved down the electron transport chain. And so this is just showing you the molecule of nicotinamide adenosine dinucleotide. And then you should see some familiar structures now. So remember our purines?
Yes.
Adenine, nicotinamide adenine dinucleotide. Adenine is one of our purine molecules. Dinucleotide, remember nucleotides? You take a purine or a pyrimidine and a nitrogenous base, attach it to a sugar, a 5-carbon sugar, and a phosphate group, nucleotide. So hopefully some of these chemical structures are starting to become more familiar to you. So this is its oxidized form, where it does not have that extra electron. And then it's going to react with some food source. So remember, with food, most of our food molecules, think about fatty acids and carbohydrates. We've got a lot of hydrocarbons, right? We've got a lot of hydrocarbons. It's really easy to grab a hydrogen off of a carbon, particularly for certain molecules. So what's going to happen here is that we're going to take protons, or hydrogen, protons plus electrons. We're going to take 2 of them from food, so we're going to grab them off of those hydrocarbon chains. And then we're going to use an enzyme, and these enzymes, we're going to find the same term come up over and over again, these dehydrogenase enzymes. Dehydrogenase means it removes a hydrogen from something. It's an enzyme that removes hydrogen. So it's going to remove hydrogen from the food source, and it's going to attach these 2 hydrogens. So hydrogen is 1 proton and 1 electron, right? And so it's going to take these 2 protons and 2 electrons, and it's going to take 2 of those electrons and 1 proton and give it to our NAD molecule. And then it's going to take 1 proton and just leave it out in the space. Okay, so we're going to find that we get a bunch of little protons floating around in our mitochondria. So we'll have proton plus our reduced form of the NAD molecule, where we've attached 2 electrons and 1 proton. So we go from NAD plus to NADH. And again, this is just how we are transporting electrons. Like, hold on to this for me for a minute. Okay, that's what the NAD molecule is there to do. It holds holds on to the electron without a great loss in energy until it can move that electron to the next molecule in the process. And this is again just looking at that chemical reaction where we take